Hi, good morning, everyone. We continue with the recording of the recitation lab for Math 102. I will share with you my screen first of all, and we will carry on. Okay. First of all, today's presentation is about the week 5 of our recitation lab of Math 102. So it essentially covers the solution of exercise at the end of week 4, and we go through special functions like logarithmic, trigonometric, inverse trigonometric, hyperbolic, which are in sections 5.7, 5.8, 5, and we'll cover overall 5 examples. So the first exercise is exercise 69 in section 5.5 from Larson Calculus. And it's what is at the end of the slides of week 4. So the problem set, find the integral by making a change of variable. We call usually substitution. And we have the integral of x squared minus 1 divided by root of 2x minus 1. And we'll upload our file. First of all, you have received the file. We'll see here that it should be week 5, not week 4. Okay, so once you uploaded the file, let's go through the process. So first of all, what we'll do, as usual, we'll define the variable x and the function f and display it to perform the appropriate integration. So here we go. We import sim_pi as SMP, and then we also call I. The small I is the integral. You see here, integral with capital I of x squared minus 1 divided by the square root of 2x minus 1. And the integral is defined with respect to x, and we'll display I. So the display is here, is what you see here. This is the integral that's the result of what we just wrote. Then we will define the new variable, which is also a real variable called small u, symbol, real variable, and we'll use it with the command transform. So I.transform, what will it do? This command will substitute 2x minus 1 by u in I, which was just defined as the integral. And the result of this substitution will be defined as k. So this will substitute here to x minus 1 by u, and then we'll display, of course, k. So this is the result of your substitution, what you see here. The integral of u over 2 plus 1/2 squared minus 1 all divided by 2 over square root of u. The whole purpose of this substitution is to get rid of this 2x minus 1, which was under the square root. Okay, so once you have performed this substitution, all we need now is to integrate. So we need to integrate the newly obtained integral. And the command simplify takes care here of the substitute of the integration. In fact, what does it do? It writes down an expression to a simpler form. And if you want to display back the result of the integration with respect to x, then we can substitute again. So we'll define here C as the constant of integration. We perform the integration using simplify, and which will be, so we simplify k plus c. We'll substitute back in the result which we get in f. We substitute u by 2x minus 1. And here we'll display f. So this is the result of our substitution and substitution back, and the result of the integration. So if you want to see the Jupyter notebook, here we go. This is our first problem. This is how we got, first of all, the substitution of x squared minus 1 by u. Okay, of 2x minus 1 by u. And then here we define C as the constant of integration. We simplify k, and we substituted back 2x minus 1 by u to get our result. Okay, so once we are done with this, let's move to the content for this week. For this week, we have 4 examples. First one is example 1, and we'll here say that if f of x is 23,415 cotangent 3x, then what is the integral from pi over 6 to pi over 4 of f of x with respect to x? So what will we do? We will use the command simplify for the integration again, which is from pi to integrate our definite integral. So first of all, we define x as the symbol variable, real variable, and f as 23,415 cotangent 3x, and capital I as the result of the integral. So this is going to be f, integral of f for x from pi over 6 to pi over 4. And we will use the command integral to produce here an unevaluated integral. Okay, so this is the result of the display. It has not been evaluated yet. To evaluate it, we'll use simplify I, and this is what will appear. So the result is 7,805 ln of square root of 2 over 2. And here is our file. There you go. So you see command line by line how this has been performed, and this is the result of our evaluation. Then we move to example 2. In example 2, we have another special function. Here we have the sine inverse, sine hyperbolic inverse. So let's say that f of x is 12,357 times sine hyperbolic inverse of 5x. And we'd like to evaluate the integral from 1 over 3 to 1 over 2 of f of x. And the command to be used here is a sine h. A sine h is used in order to define this sine hyperbolic inverse. So it's like arc sine hyperbolic. It calls the inverse sine hyperbolic function. So we define f as 12,357 a sine h of 5x. And for our integral capital I here, we define it as the integral from, what is this? Rational of 1 and 3. That's 1 over 3. So this defines as something new. It writes a rational, a fraction, 1 over 3. And the upper limit of our integration is 1 over 2. So we have another command to learn here, rational. Sometimes you need to use fractions. So we use the command here to display, to define I, will display it. So that's the result of our display, what we have here. We make sure that we have the right integral that matches the exercise, and then we will evaluate it using simplify. So this is the result of your integration. No. Okay. Now, there is an observation here. This doesn't give me a proper value. An exact value, numerical value. And we'll have to find an answer to this, how to do this. And this is what we'll see in the next example. Properly calling the float command. This will convert that number, the value we got after simplification, to something which gives more information about the numerical value. We'll move to example 3. And here we have f of x, which is 2 over x root of x to the power 4 plus 1. And we'd like to just find the antiderivative of this function. And it's going to be normal to have the antiderivative containing the inverse of sine hyperbolic, because we know that the derivative of the sine hyperbolic is, by the chain rule, is if you have sine hyperbolic function is u prime over square root of u squared plus 1. So the sine hyperbolic inverse of x, its derivative is 1 over square root of x squared plus 1. So first of all, we define one function, which is f as 2x divided by square root of x to the power 4 plus 1. We'll define our integral. Okay, this is an indefinite integral here, unevaluated. And we have a symbol c, which is the constant of integration. And just we'll simplify I plus c. And of course, here since we have no limits on our integral, this is an indefinite integral. We'll have just sine hyperbolic, arc sine hyperbolic of x squared as the result of our integration after simplification. So it gives you this function. Okay, for the Jupyter Notebook file, here we go. I think we left at example 1. That was example 2. The integration from 1/3 over 1/2 of 12,357 sine hyperbolic inverse of 5x. And this is how it's running. Integral from 1/3 as a rational to 1/2 as a rational of f of x dx. And this is what we just got. And for our example 3, this is what we were just explaining as the integral of 2x divided by square root of x to the power 4 plus 1. Okay, with the concept of integration and just the expression here of the entire derivative with a constant. So the result is arc sine hyperbolic of x squared plus. This note is added just a reminder to explain why we got such an entire derivative. Now we move to the next question, which is example 4. And in example 4, we have to define f of x as ln of x squared plus 1 and integrate from 1 to e f of x. So in this example, there was in the first slide, there was a tiny misplaced image. We corrected it. So we'll say that, first of all, we define f as what? As the ln of x squared plus 1, and I as the indefinite integral of f. So here we're displaying it, the integral of ln of x squared plus 1. That's the display. And when I say I that do it, what we'll do, it just performs the integration. So the result is x ln of x squared plus 1 minus 2x plus 2 arctan of x. Okay, now we'll ask also to integrate this function from 1 here, from 1 to e. So it's exponential of 1, in fact. So we'll use this command to produce a value for the different integral. Notice the difference between integral with capital I as a command and integrate, which will give you a value for your integration. Okay, so that's very important to understand. So the result of the integration here is brought to the value val, and we'll display val. So this is the result of this display, and you'll see that it doesn't look as a numerical value at all. It contains pi, e, ln of 2, arctan of e, ln of 1 plus e squared. And if you want an exact or just, a more, let's say, informative numerical value, we'll convert val to with using a float. So we use the float command to get the numerical value, and this is what we get, 2.517. Okay, so you can repeat as an exercise for you the same command added for the previous exercises, and you will have the exact numerical value, or let's say more precise numerical value. Okay, we'll move to example 5. In example 5, what do we have? We kind of modified a little bit example 4, and we'll check now the difference when 2x is placed in front of ln in example 4. And here it reaches back to week 4 material, where we could use the substitution u equals x squared plus 1. Okay, so here the most important thing here, the objective of this modified problem is to combine week 4 material with week 5. And remember here that the entire derivative of ln of x is s ln of x ln of x minus x plus c. Okay, so if we assume that f of x in our example 5 is 2x ln of x squared plus 1, then here the integral from 1 to e of f of x would be just would be written as the integral from here, if we perform the substitution, u will start from 2. Yeah, u will start from 2, and because x will start from 1, and u will start from 1 squared plus 1 to 1 plus e squared. So that's written in terms of u. That's after the substitution. Okay, and of course, the result of this integration is just, you can use this antiderivative, you just substitute x by 1 plus e squared, and you get what you want. The two upper and lower limits of the integral. So here is our small command window. F is 2x ln of x squared plus 1. I define my integral as the integral of f from 1 to e. I'll display I, and I'll simplify I. And this is the result of integration. So this is exactly what we got just analytically without performing anything, just by substitution. And the result sounds really good. Okay, so for example, 4 and 5 in our Jupyter notebook, here is the result. For example, 4, where we had ln of x squared plus 1 to be integrated from 1 to e. We defined I as an integral, and we performed the integration using the do it command. And then we evaluated this integral using the small I integrate from 1 to e of f. We display the value, which is here, and then we asked for a more numerical or more precise numerical value for the value of that using the float command. Okay, and example 5, here we go. We have 2x ln of x squared plus 1. We defined our integral from 1 to e of 2x ln of x squared plus 1. We display the integral and we just simplify. Okay, and I added a note that, remember, with the substitution, this is exactly what we would have expected. Okay, here I'm performing the substitution just to show that what we got by direct integration is exactly what we could have obtained using the substitution. So I'll define u as my new variable, and I'll substitute x squared plus 1 by u in I, and I display k. So this is what we got after the substitution. Okay, and here k, the width, will just display it again because it couldn't do much more. If you want, you can just add a float of k, and you will have a numerical value. Okay, so I hope everything is clear now. This is the result of the substitution and the slides. Thank you very much for following. We'll get back next with the recording for week 6. Thank you very much.